Hello everyone. Today I'm going to be considering a request that I had from a viewer about using the precise definition of a limit, that is the epsilon delta definition of a limit, to show that a limit may not exist or that the limit of a function is not equal to a particular number. I'm going to do a couple of these examples in separate videos, and I'll start with a pretty simple one. This is actually just going to be a video that I did quite some time ago using the epsilon delta version of a limit, but I'm going to show that the limit of this function to a particular value of x is not equal to something that we know it's equal to. Okay, so in a previous video, I showed that the limit of this polynomial when x approaches 2 is actually -2. We did this using the epsilon delta definition of a limit. If you want to compute this directly, I mean, it's a polynomial, so just substituting in x equals 2, you can see very quickly it's equal to -2. What I want to do is show that using the epsilon delta version of a limit that this is certainly not going to be equal to 3. So the way I'm going to do this is first I'm going to write down the precise definition of a limit in terms of epsilon delta. And rather than proving that statement, which of course will be impossible when the right-hand side of this is equal to an incorrect value, I'm going to write down the negation of the statement we're trying to prove and work out logically what it is exactly we're trying to show. Okay, so this here is what would be the precise definition of the limit. This is the precise statement we would want to prove if we had an equal sign here. Those two statements would be equivalent. In some previous videos when I wrote this down, I didn't include this universal quantifier for x. It's kind of implicitly understood to be there, but writing it there explicitly will help in showing what I'm trying to do here. Now, we're never going to be able to prove this because this statement is incorrect. If I had instead put a +2 here, then we'd be able to prove it. So what I want to be able to prove is the negation of this statement. So one thing to understand, you may not know this, you may only have an intuitive understanding of what these symbols for all and there exists mean, but I'll put this in quotation marks. There are relations between the existence and the existence quantifier and the universal quantifier. Basically, in a symbolic statement like this, anywhere you see the universal qualifier, that's logically equivalent to the negation of the existence of something with a negation after it. And so when I negate this entire thing, what's going to happen is this is going to flip to an existence, but then it'll produce another negation, which will then kind of move on to the next part of the symbol, but then we'll have a negation of the existence, which turns into, we're negating that, turns into for all, and so on. So the thing that I actually want to prove here is the following. Okay, where this negation symbol is applying to this entire logical implication statement. Now, if you think about what an implication like this means, or if you in fact just write out the truth table of the implication operator, this is the same as the following. Okay, so when you have an implication statement like this, and negate it, then that, in this example, it turns into exactly this. So what do we want to show here? We want to show that we can find some value of epsilon, some positive value of epsilon, such that for all delta, there exists some x where, no matter how small delta is, we're able to find an x which is close to 2, so as close as we want. No matter how close we get to 2, there is some value of x close to 2 such that this expression is, significantly different from 0. So it's at least epsilon away from 0. Okay. How do I want to do this? Let me think for a second here. I might have to do some rough work, mess around with this expression, maybe factoring it in some way or something like that. But yeah, let me do a little bit of rough work and see what I can come up with. Okay, so I think I've essentially figured this out, but let me go through the full argument here. I mean, any value of epsilon here is going to work, but in order to make this really explicit, I'm going to let epsilon be equal to 3. Okay, and now suppose delta greater than 0 is given. I'm going to let x be anything in the set 2 minus delta over 2 to 2 plus delta over 2. But I don't want to be too far away from the number 2. So I'll also say it's between 1 and 3. So this set, I guess I should remove the singleton 2 as well. Okay. So x is somewhere around 2, but not too far from 2. This set is always non-empty because delta is positive. So what can we write now? I have x squared minus 3x minus 3. This is equal to x squared minus 3x plus 2 minus 5, which is x minus 2 times x minus 1 minus 5. I can write this as 5 minus x minus 2 times x minus 1. Use a version of the triangle inequality. This is greater than or equal to 5 minus x minus 2 in absolute values times x minus 1 in absolute values. And because of the way I've chosen x, x has to be between 1 and 3. So x minus 2 has to be between negative 1 and 1, and x minus 1 has to be between 0 and 2. So this product, the largest that that can be, is equal to 2. So this thing has to be greater than 3, which is epsilon. Okay. So I ended up working out that this thing is greater than or equal to one particular value of epsilon. It doesn't matter how small or doesn't matter how delta is chosen, there will be a value of x which has our function. There will be some value of x which has our function far away from the proposed value of the limit. I guess I could show graphically kind of what's going on here as well. I don't know, what does this function look like? X squared minus 3x, so something like this. We're taking x approaching 2. I don't know if this is to the left or the right of the vertex, doesn't really matter. And we're saying that, we're trying to show that this can't possibly be equal to 3 as we approach 2. So basically what we're doing is we're putting we're showing that there's some interval. We're showing that there's some interval around 3, like this, such that there's, in any neighborhood around the value of x we're considering, there's always going to be points on the graph of the function which are outside of this interval. So that's basically it. It's, I'll admit, it's a little bit bizarre to be trying to prove that the value of a limit is not equal to a particular number. Some of the examples that I'm going to do in other videos very shortly kind of do require that, but usually this type of argument would be used to show that a limit does not exist, not that a limit is not equal to a particular value, especially when you know what the correct value of the limit is supposed to be. So this is kind of weird, and it didn't go as smoothly as I thought it would. But the other examples that I want to do along the lines of showing limits don't exist or showing a function is not continuous at a point, I think those should be a little bit smoother, and they still do rely on the epsilon delta version of the limit or of continuity. Anyway, thanks for watching. See you in a future video.